Dr. John Replogle has worked for several decades to improve flow measurement technology for irrigation canal systems in California and worldwide. Flow metering can identify good irrigation management and likewise point out where the management needs help. Drip and sprinkler irrigation system management has industrial support. This support is not as easily available for canal systems, usually associated with surface irrigation, that is still dominant worldwide and in California. Researchers have shown that with proper selections of crop, soil, and water flow rate control, highly effective water conservation is possible and economical. Here, in this video, we will follow canal water delivery as it finds its way to a particular farm and onto fields and crops. Farm delivery automation with flow measurement technology can help to minimize unwanted deep seepage, prevent polluting runoff, and reduce the amount of water that the farm operator needs to request. This would allow the unused delivery for redistribution to other needs. When the water supply canal reaches the farm measuring location, the automation controls the water delivery opening to the farm. This can typically be a gate on the entry to a pipe under the canal maintenance road. The automation adjusts the gate to the required flow rate. If the delivery fluctuates, the gate automation adjusts the gate to maintain that constant flow until the delivered water order is completed and the gate is closed. The constant flow rate control allows the farm operator to apply an accurate volume to a field plot based on timing. Usually, large flow rates onto level fields in a short time are very effective, particularly when coupled with soil and crop root zone factors. I'm John Replogle. I'm going to explain some of the systems that we use to measure flow under large culvert-type pipes that go under canal maintenance roads. Without any added internal conditioning elements, it would take about 300 feet of pipe to control the turbulent jet that is formed when the farm gate is first opened. With our patented engineered flow conditioning elements mounted inside this 24-inch pipe, we do it in a very short distance, around 40 feet. The purpose of conditioning the flow is to control the natural spinning, swirling, and twisting of the jet. This will produce a near uniform stream just before the propeller meter, which is seated at the end of the pipe. The propeller meter can only accurately measure flow if the water is properly conditioned. Here, we see a partially open canal farm gate and a strong jet coming under the gate, with the flow proceeding to a 1/4 diameter high weir plate. This tames the jet. The jet spoiler converts substantial energy by exploding the flow across the pipe. Here, the jet approaches a large opening orifice. The jet, moving through the orifice, pushes the flows towards the center and cross-mixes them, stopping any jets from moving down the sidewall of the pipe. The flow then reaches a second orifice, accompanied by some weed-shedding, straightening veins that stops the spin and produces a uniform flow across the pipe, preparing it for the propeller meter further downstream. The flow is now conditioned so that the meter can detect a velocity at the center line of the pipe that represents the entire cross-section of flow. Now, we see a simulation of the stream coming through the pipe that has all our appurtenances I spoke about earlier. It first comes out of the gate, hits the weir plate, then the orifices and the straightening veins, and onto the propeller meter. Here's an elevation view of the same hydraulic actions. The insertion-type electromagnetic meter would receive similar jet taming and weed-shedding treatment. It is applicable for pipes up to 12-inch diameter.
This is a long-throated plume that is calibrated by the process wind flume that is maintained by the Bureau of Reclamation in Denver. And what I've installed here is a sill and a ramp. And some people call it a ramp flume, some call it a, well, otherwise, Replogle flume, whatever. But anyway, what we're doing is we're measuring the head of water through the little holes in the static pressure tube that's being siphoned into this cup. And this is the head we need upstream. That's where a wall gauge would be ordinarily. And we're bringing, and rather than using surveying instruments, I'm just bringing that siphon level into this cup, which is above the, what we call the sweet spot. It's about 1/4 of the way up the flume and in the middle. So it doesn't matter if it's tilted a little bit or a little, any direction, it's fairly tolerant. So I now have measured that distance from the floor into the cup. In this case, I happen to have access to a point gauge, so I use it. Otherwise, you can use a sharpened piece of dowel stick and a ruler, and you can get within a millimeter. That's what we use when we don't have access to a nice point gauge. Anyway, and the cup can be made. I've made cups out of Coke bottles, so the cups can be made. Don't have to be this precision here. So that's about the whole story.
So how do you then take the measurement and turn it into a CFS measurement?
Well, I have to take this depth if the water is above the sill here. I have to take these two. The depth up here is like here, and that depth then is I've entered in the table that is computed by the wind flume, and that's where I get that number. Convert it to CFS.
All right. Can you show us what is running right now? What CFS is running?
Let me see. When I subtract the 0 away, I'm ending up with a net of 0.733 feet of depth. And when I put that into the computer table over here, .733 gives me 10.12.
Can you point to that one on the screen?
10.12
Thank you so much.
CFS.
So, Dr. Replogle, you have taken a measurement with this sophisticated setup here using a point gauge, and we now have an electronic verification of the micrometer reverse propeller flow meter that's inside our pipe, and they're reading there at 10.5 CFS. You're reading here at 10.2 CFS. Where does that put us in relation to the factory claim of plus or minus 2% in the laboratory?
I'd say it was very good because, as I say, my 10.2 and they're 10.5, and I'm definitely low because of leakage, so I'd have to add a little bit. So they're within 2% of me already.
So this is then a verifiable field experiment that the micrometer reverse propeller flow meter is at plus or minus 2%.
I'd say it's well within their. I think that it should be a verification of their claim.
Thank you so much, Dr. Replogle.